Welcome to Investigation 1.3. This is fractional growth patterns. In this, we are going to be looking at situations where our growth pattern is not doubling or tripling or quadrupling. Instead, we might see a growth of like 1.5 each time. So instead of it being 100, it might be 100 to 200, it'll be 100 to 150, and 150 to 225 or something like that. So fractional growth patterns shows more real life situations. It's not often that things double. It's more often that things are a little more messy with fractions. So our focus question for this investigation is, how is the growth factor in this problem similar to that in previous problems, and how is it different? So be sure to write that down when you're doing your missing page, and let's get started. So we've been looking at situations where we've been looking at growth patterns for doubling. So if we look at plan 1 for the peasant, we were seeing in the first square there was 1 ruba, second square there was 2, in the third square there was 4, in the fourth square there was 8, 16, 32, 64, 128, and so on. And we noticed that the peasant got really, really, really rich after a while. For mold growth, we are also seeing an interesting pattern. We saw a pattern that related to this equation. We had mold was equal to 50 times 3 to the nth power. And so we got some information from that. Just one moment, there will be a little bit of math magic. And so we saw how the growth in this one happened in triplets. We saw a tripling of things. We saw essentially things go times 3, oops, that's a 3, times 3, and so on, whereas this other one was a times 2 pattern. So there was various equations that we were working with. Well, now our question is, how else can we look at our growth pattern? Like, how else can we discover our growth? We can look at it as saying, well, 1 multiplied by 2 gets me 2, 2 multiplied by 2 gets me 4, 4 multiplied by 2 gives me 8, and so on. But if we also wanted to, we could simply say 32 divided by 16 would get me 2, and 16 divided by 8 would get me 2, and so I could see a pattern in that realm develop. We could do the same thing for the mold growth and say, all right, well, 36,450, 36,450 divided by 12,150. If I were to divide those two things, I get 3. If I do 12,150 divided by 4,500, I also get 3. And so I could develop a pattern like that. This method of dividing can be really helpful when we're looking for the fractional difference. So let's think a little bit more on, now that we know of how else we can get growth factors instead of just, we can either multiply or divide our outputs to get our growth factor, which can help us with our equation. So let's look at fractional growth. Let's understand this a little bit. We have a grasshopper situation. So in my backyard every year at the beginning of the summer, I end up with some grasshoppers, and I notice these grasshoppers get more and more extreme as the summer goes on, and they eat all the leaves off my vegetables, and then my vegetables start to die, and it's horrible. Well, I'm making up a situation. Maybe in the first week, I noticed that we have 10 grasshoppers. In the second week, there's 18. In the third week, there's 32. In the fourth week, I have 58. I'm amazing at counting grasshoppers. In the fifth week, we have 105. In the sixth week, 189. And in the seventh week, we have 340 grasshoppers. So in just a little less than 2 months, I'm already at so many grasshoppers that my garden just gets inundated. Well, how can we find the growth factor of this situation? So we need to do a little bit of math. Our focus is right now, what is that growth factor? So we're looking at this question. What is the growth factor? So it's hard for me to figure it out straight from here. I see that 8 is kind of added to that 10, but eventually, so this is like a plus 8 pattern, and then 18 to 32 is plus 14. So I'm not necessarily seeing any sort of rhyme or reason to this increase. So we also know that growth factors typically happen in multiples or division. Or with division. So let's take a couple of numbers. I'm going to take 105 and 58. And I'm going to divide those two numbers to find my growth factor. If I divide 105 by 58, I get 1.8. To write that as a fraction, I could write it as 9/5. 1.8 equals 9/5. Let's see if that's the same for some other numbers. 189 divided by 105, 189 divided by 105, 189, sorry, divided by 105, I also get 1.8. 189 divided by 105 gets me that same 1.8, which could also be written as 9/5. Let's see if that works for the 10 to 18. If I multiply 10 by 9/5, I should get 18. And if I did 10 times 9/5, I do get 18. So that's kind of cool. 18 times 9 divided by 5 gets me 32.4, or 32 if I were to round. So I'm seeing a growth factor of 9 divided by 5, or 1.8. That is a fractional growth pattern. As well, we can also say we need to find what is the initial population. Our initial population is where our x value equals 0. So we need to go back in time to find out what it is for 0 weeks. So we need to divide 10 by 9/5. I guess it's not necessarily, we don't need to divide 10 by 9/5. We need to divide 10 by, or we need to multiply 10 by 5/9, and we end up getting 5.6, or we could round that to 6 grasshoppers. So our initial population, when x equals 0, y, or our grasshopper population, equals 6. So there's our y-intercept, and here, this 1.8 is our growth factor. So now let's create an equation for this situation. Our equation, if we remember right, if we were to look in on this, the y is our output, our x is our input. So we have essentially out and in. Our a is our initial population, and our b is our growth factor. So if we were just to plug things in, we'd have our output, which is grasshoppers, is equal to our input of 1.8, not our input of 1.8, sorry, our initial population of 6 times our grasshopper growth factor, which is 1.8, and we have an exponent of weeks. So here is our equation. Now, I have another question. What happens, or how many grasshoppers will there be in 20 weeks? So we need to figure out how many grasshoppers there'll be in 20 weeks. We have an equation. We have 6 grasshoppers as our initial population times 1.8, and we have 20 weeks for our exponent. So let's do a little bit of math. And what we'll end up seeing is some massive growth. It'll end up being 764,894 grasshoppers. Just 1.8 raised to the 20th power. Doing that, I get a crazy number of 127,842. So I'm just multiplying that 6 times because we have an initial population of 6. So we have crazy growth. If these grasshoppers were to go untaken care of for 5 straight months, we'd have an epidemic on our hands, which would be super bad. So let's move on and play around with this whole concept. And let's suppose that the grasshopper population in Livingston can be modeled by this equation. The population is equal to 10 times 1.1 to the n value. So that means we have our output and our input. We have an initial value of 10, an initial population, and we have a growth factor of 1.1. So our question now is, for Livingston, they apparently have a slightly slower growing grasshopper population. Maybe the wind plays a factor, who knows. But in how many weeks will the population double? So that is our goal and our focus for right now. So looking at this information, one of the big things to be able to figure out if a population is going to double or when it's going to happen is to think about what is happening with your growth factor and how it's growing. So we have this situation where we have a growth factor of 1.1, and so we can make a table and see how it grows. So if we were to have 1 month, our 1.1 is just going to be 1.1 to the first power, or 1.1. We can see for the second, we would have 1.1, oops, that's not 1.1, that's 11, sorry. So 1.1 squared, which is 1.21. For 3, we do the same thing, 4, 5, 6, 7, and we'd figure out in how many weeks this population is going to double. So 1.1 to the 1.1 cubed would be 1.331. 1.1 to the fourth, oops, is 1.4641. We can do the same thing and so on. So I'm going to do a little math magic. I'm going to just plug these numbers in just 1 second. So I've done a little math magic. You can see that I filled in the rest of the table. We have 1.61 for 1 to the 5th. We have 1 to the 6th, 1 to the 7th, 1 to the 8th. And so our whole focus is in how many weeks will the population double, or how many weeks will the population be double or more. And if we look at our growth factor grows like multiplies by itself 1.1 over and over until the 8th week, when that growth factor has turned into. And what we can find is in 8 weeks, at 8 weeks, we have a growth factor that has doubled itself so much, or it's multiplied by itself so much, that it's now 2.14. So let's see if that actually doubles our population. So if we were to multiply that by 10, we would end up with, if we had 10 times 1.1 to the 8th power, we'd end up with 21.44 grasshoppers. So that's kind of cool. We can see that population doubling in 8 weeks. Apparently Livingston doesn't have as much of a grasshopper problem as we do in Bozeman. Then it also asks us, in how many more weeks will that population double again? So it took initially, it took initially 8 weeks for the first doubling to occur. Let's make a prediction that maybe in 16 weeks, the second doubling will occur. So instead of it being 20 grasshoppers, we're going for 40 grasshoppers. And so this happened in 8 weeks, and 40 grasshoppers, if we made a prediction, could happen in 16 weeks. So let's see if that happens. If we had 10 times 1.1 to the 16th power, would we end up having the same thing? And in the 16th week, we have 45.9. So it's gone a little bit more than doubling. If we do 10 times 1.1 to the 15th, we have 41 grasshoppers. So there's the doubling. It happened 8 weeks, or it happened 7 weeks after that 8 weeks. So if I think about it, we have 1, 2, 3, 4, 5, 6, 7 weeks after that first week, and now we have a few more and we get 15, so we got the doubling there. So playing around with exponents can also help you find when things double, when things will triple or quadruple or whatever it may be. So the job now is to play around with this concept of fractional growth patterns and work on investigation 3.1 and finish the homework for 3.1. I hope this helped, and I will see you later. Bye.